Okay, May, June 2021, paper 4, variant 3. Hmm. Question 1 shows a load suspended from a spring. The value of the spring constant K is zero point 0.2 newtons per centimeter. The spring reaches its limit of proportionality when the load is 15 newtons. Okay, so this is the limit of proportionality when the load is 15 newtons. Can I find the extension when the load is 3 newtons? Can I find the extension? Yes, we have the equation F equals kx. Okay, so this is the equation F equals kx. To find the extension, which is x equals F over k. So what is the force? I want the force at 3 newtons. 3 over 0.2. So that's it. That's all you need to do. 3 over 0.2, which is 15 centimeters. 15 centimeters. Explain what is meant by the term limit of proportionality. Limit of proportionality is a point at which, if reached, okay, or if exceeded, okay, a point at which, if you exceed the point, this load, the spring will no longer be directly proportional. The spring no longer obeys Hooke's law. The spring no longer obeys Hooke's law if you exceed this point or if you reach this point. So up to this point, it is directly proportional. Up to this point, what are the two things that are directly proportional? Up to this point, the force and the extension are directly proportional up to this point. So you have to say that the force and extension, force and extension hmm, are directly proportional hmm, up to this point, up to the limit of proportionality of proportionality. Hmm. Okay. On figure 1.2, sketch an extension load graph for the spring. Label the limit of proportionality with the letter L. So we need to draw a limit, or we need to draw a straight line first, which is directly proportional starting from the origin. Okay, starting from the origin. Okay, so the first part is quite easy. We draw a straight line using the ruler. This is a straight line, definitely. Okay, draw using the ruler. Okay, at this point, we can name this point, for example, the L, the limit of proportionality. You can name after the limit of proportionality. hmm, After the limit of proportion, what happens? Is it any longer? Is it direct proportion? Can I continue drawing a straight line? No, definitely, I will not draw a straight line. I will have to draw a curved line. In which direction? Towards the load axis or towards the extension axis? Definitely towards the extension axis. So after the limit of proportionality, it kind of curves towards the extension axis. Why? Because you no longer need that much force to extend the spring. Because the spring has been broken. The load is pulled down a small distance between its equilibrium position to position A. Okay, so it's pulled down between its equilibrium position to position A. The load then moves up and down between A and B, keeps on oscillating between A and B. Describe the energy transfers which occur as the load moves from A to the equilibrium position. The equilibrium position is somewhere in the middle. This is the equilibrium position. So as it moves from A to the equilibrium position, what are some of the energy transfers? What are some of the energy transfers? So at A, it was kind of extended. We kind of pulled the string downwards. It had what type of energy store? It had elastic potential energy. It had elastic potential energy as you pulled it downwards. And then as you release it, as it's now moving upwards, so this elastic potential energy is now being converted to what type of energy? To gravitational potential energy. So as it's moving upwards, it's being converted from elastic to gravitational potential energy. From elastic, and definitely you can say strain instead of elastic, okay? From elastic, let me write it down again. Elastic to gravitational potential energy as it's moving upwards. From the equilibrium position to point B, to point B. So at the equilibrium position, there is no elastic energy. خلاص, it's no longer stretched or compressed. It is no longer stretched or compressed at the equilibrium position. As it's now moving upwards, as it moves even further upwards, it now has some kinetic energy. At this point, it now has some gravitational potential energy and some kinetic energy because it's still in the process of moving. So you can say that it can convert some of the kinetic energy to, okay, to again elastic potential energy or to more gravitational potential energy. Okay, so هنا you can say kinetic energy, okay, from kinetic energy to gravitational and elastic potential energy. Why elastic potential energy? Because it's being compressed. As you move upwards at position B, it's being compressed, so it has more elastic potential energy. Hmm. Question 2. Figure 2.1 shows a bookshelf with two groups of books, A and B. You have A and B. Um, Explain why the pressure exerted, okay? Explain why the pressure exerted on the shelf by the books in group B is less than the pressure exerted on the shelf by the groups in or by the books in group A. It's quite simple. This is a quite simple answer. Why? In B, what happens to the area in contact? What happens to the area in contact? So we can say that the area in base, the area of the base, increases. So the area of the base increases as the area increases. What happens to the pressure? Pressure decreases for the same force. That's all you need to do. That's all you need to say. Okay, so in B, the area, hmm, the area in contact, or the area of the base, let's say the area of the base, which would be better, of the base increases. As you increase the area of the base, the pressure decreases. Why? Because they are inversely proportional, okay, for the same force exerted. Force exerted. Definitely, if the force increased, then the pressure would have increased. But since they are the same weight, then the force will be the same. Calculate the pressure exerted on the shelf by the books in Group A. Okay, Group A. The mass of each book is 0.52. Okay, you have 6 books in each group. You need to think about this very carefully. You have 6 books. Mass of each book is 0.52. So first of all, pressure equals force over area. We need to find the force. Force over. You need to find the force, which is the weight. Basically, weight equals mg. The mass, the total mass is 6 times 0.52. So 6 times 0.52. This is just the mass. And then you need to find the weight. So you multiply by 9.8. So what's 6 times 0.52 times 9.8? Times 9.8. This gives you a weight of 30.57, or you can just say 30.6 newtons. 30.6. This is the total force, the total weight. Good. What is the area? The area in contact would be length times width, which is 1.3 times 6 times 21. 1.3 times 6 times 21. Let's calculate it. So it's actually 1.3 times 6. Why? Because you have 6 of these books. Times 21. What's 1.3 times 6 times 21? 1.3 times 6 times 21. This would give you a total area of 163.8. Okay, 163.8 centimeters cubed. but definitely we need to change them, or we need to change this to meters squared. Why? Because the pressure is in pascals, and pascals is newtons per meter squared. So how can I convert this to meters squared? By dividing by 100 squared. You have to divide this by 100 squared, which would give you a very small number, 0.01638. It's a small number. Okay, I don't care. I don't really care. 0.01638. This is the total area. So you have the weight, you have the force, and the area. It's okay. So it's 30.6 divided by 0.01638. Okay. 30.6 divided by this area would give you a total force or a total pressure of 1868. You can just write it down as 1870 pascals. 1870 pascals. I know the numbers are a bit tricky, but again, this is variant 3. Variant 3 questions are about being tricky. Okay, it's not that difficult, it's just about being a little bit more tricky. A diver dives to a depth below the surface of the seawater where the total pressure is 3 times 10 to the power of 8, which includes, total pressure includes the atmospheric pressure, which is 1 times 10 to the power of 5. The density of the seawater is 1030 kilograms per meter cube. Calculate the depth of the diver below the surface of the sea. How can I find the depth of the diver? First of all, pressure equals rho gh. Rho gh. The pressure of the water, okay, when I'm talking about pressure equals rho gh, I say pressure equals rho gh. This is the pressure of the water. This is never the total pressure. This is the pressure of the water alone. So how can I find the pressure of the water alone? We need to subtract 3 minus 1, which would be 2 times 10 to the power of 5. So this is basically the pressure of the water, 2 times 10 to the power of 5. Is equal to rho, which is the density 1030 times g times 9.8 times the height. Can I find the height? Yes, it would be 2 times 10 to the power of 5 divided by 1030 times 9.8. Let's find out. 2 times 10 to the power of 5 divided by times 1030. This would give you a total depth of around 20. Around 20 meters. Again, as we said before, each 100,000 pascals is around 10 meters. Around 10 meters. 100,000 pascals means around 10 meters below the surface of the water. A car travels at a constant speed on a horizontal straight road. The driver sees an obstacle on the road ahead. The distance traveled in the time between the driver seeing the obstruction and applying the brakes is the thinking distance. So once you see an object in front of you, you try to apply the brakes almost instantly. Okay, we try to apply the brakes almost instantly. But again, we are not robots. Okay, we cannot do anything instantly. There has to be some delay, which we could call in this case the thinking time, which would cause a thinking distance. This time delay would create a thinking distance. Okay. Explain why is there a thinking distance, or why the thinking distance is directly proportional to v. Why is it directly proportional to v? Because thinking time, distance equals speed times time, or speed equals distance over time. So whenever I'm talking about, if the speed is constant, okay, if the speed is constant and the time or the distance is constant, then the time will also be constant. If the speed is constant, so the time will be constant. So this is part of the answer. If you want to think about it this way, okay, the time taken to think about something, okay, it's around, I guess it was around 0.4 seconds, something like that, or 0.2 seconds. This is the delay we take, okay, to just see something in front of us and start taking an action. There has to be a delay. I guess it was around from 0.2 to 0.4 seconds. This is the time delay, which is always constant, which is always constant. So the time or the thinking time is always constant. Okay, the thinking time Okay, the thinking time is constant. Again, it's around 0.4 seconds, I guess, 400 milliseconds, something like that. When the brakes are applied, okay, when the brakes are applied, the car decelerates uniformly to rest. The frictional force applied by the brakes is constant. Think about this very carefully. The frictional force is constant. The distance traveled between first applying the brakes and the car stopping the braking is the car stopping is called the braking distance. Again, so when I stop or when I apply the brakes until I stop, I'll call this distance what the braking distance. Okay, now why is the braking distance proportional to v squared? Why is the braking distance proportional to v squared? So the first one, you talked about the thinking distance and how it's proportional to v, and we said speed equals distance over time, distance over time. So yeah, time would be proportional to the speed, which is okay, 1 mark. But in this question, why is the braking distance proportional to v squared? We need to apply some equations. How can I apply some equations? Initially, the car was moving with some kinetic energy. V squared. Okay, the only V squared we have in our syllabus is what? Is in the kinetic energy. So half mv squared. This is the kinetic energy of the car. Initially, it was moving with the kinetic energy of whatever amount of joules. And then as you apply the brakes, this kinetic energy is being converted to what type of energy? It's being converted to what type of energy? It's being converted to mostly thermal energy due to the braking. It's being converted to the braking, the thermal energy, friction and whatnot. And you have a force being applied and the distance being moved. The car moves a distance which is called the braking distance, and there is a force being applied. Force and distance. Doesn't this ring a bell? Yes, it does ring a bell, which is called the work done. So we might say that the work done to stop the car would be equal to the initial amount of kinetic energy in the car. So, kind of, let me write it down. Work done, which is the force times distance moved, braking distance, would be equal to half mv squared. The mass is constant, definitely. So that's why the braking distance would be proportional to the velocity squared. We need to write that down. That's all we need to write down. That's all you need to write down. Let me write it down in hopefully simpler words. Let me write it down in hopefully simpler words. Initially, the car had kinetic energy, which was equal to half mv squared. Initially, the car is moving. Okay, this is quite sensible. The car was moving with half mv squared. To stop the car, to stop the car, work needs to be done. Work needs to be done. Okay, work needs to be done to decrease this kinetic energy. To decrease the kinetic energy. To decrease the kinetic energy. So we need to do work on the car to stop it. Okay, you need to do work on the car to stop it, and this work done would be equal to, you might say, work done equals force, okay, times distance. Force times this. That's it. That's all you need to think about. Okay, so it's all about energy transfers. It's all about energy transfers. The distance moved. Okay, the distance moved. So this distance would be the braking distance. You don't need to write this. Okay, this would be the braking distance, which would be directly proportional to the velocity squared. Why? Because the mass is constant and the force applied is also constant. The force applied is constant. So they are both proportional. Okay? Again, as I told you before, um, paper unit, sorry, variant 3 questions are all about being tricky, not about being very hard. No, it's about being tricky, about trying to read between the lines. Yeah, the car is traveling at 22 meters per second. The thinking distance is 15 meters. Calculate the time. Okay, this is a very simple question. Speed equals distance over time, or this time equals distance over speed. Time equals distance over speed, so the distance is 15 and the speed is 22. 15 divided by 22 would be 0.68 seconds. Not dollars, seconds. Okay? Yeah, 0.68 seconds. The car has a mass of 1,400 kilograms. The time taken after the brakes are applied is 2.1 seconds. Calculate the force required to stop the car. How can I find the force? How can I calculate the force? Any ideas? Find the force and time and mass. Probably you need to find the change in momentum. No, not force. Force equals mass times acceleration. Okay, you can do it. You can say force equals mass times acceleration. It's not wrong. If you can find or if you measure the deceleration, yes, definitely you are 100% correct. You can do this. You can solve it that way, or you can just say that force times time impulse equals mv minus mu mv minus mu, which is again the same equation. So go ahead and use force equals mass times acceleration if you'd like. Okay, mv and mu. What is the velocity? The velocity was 15. The velocity was 22. So basically, you're saying 1,400 times 22, and you can just consider this to be zero. To find the force, you need to divide by time. Okay, so divided by the time, which is 2.1 seconds. 1,400 times 22 divided by 2.1, which would be, let me calculate it, 1,400 times 22 divided by 2.1. 14,666, which could be 14,700 newtons. Please do not forget the units. Hmm. The latent, this is cancelled. Okay. Okay, this is cancelled as well. I. On hot days, sweat forms. Okay, we can solve this question. Hmm. The sweat forms on the skin and then evaporates. Explain in terms of molecules how the evaporation of the sweat cools the person. Okay, sweat is a very important process to help cool us down. How can I describe what happens in evaporation? The most energetic molecules escape from the surface, leaving behind the least energetic molecules, uh, decreasing the average temperature and causing a cooling effect. Most energetic molecules escape from the surface, leaving behind, hmm, leaving behind the least energetic molecules, hmm, decreasing the average temperature, decreasing the average, and causing a cooling effect. Explain why this process is more affected when a wind is blowing. Why do we feel a lot more of this cooling effect when the wind is blowing? What does the wind do? What does the wind do? Hmm. It carries more molecules from the surface. Okay, it causes a greater rate of evaporation. Okay, it causes a greater rate of evaporation by carrying hmm, by carrying more molecules, more molecules from the surface. That's it. Okay. Hmm. Figure 5.1 shows a wave on the sea approaching a harbor. Okay. On figure 5.1, draw three wave crests in the harbor. So as they pass through the gap, what will happen? We need to draw the waves after they diffract. Diffraction. How can I draw them? How can we draw them? Definitely, this would be considered to be a narrow gap. Narrow gap. So using your compass, how can I use my compass? The pointy edge has to be in the center, and then I open up the compass onto the first wave front and draw a semicircle on this side. And then again, the pointy edge is on this in the center of the gap. Open up the compass hmm, to the second wavefront and rotate the compass and draw another semicircle on the other side of the gap. And then repeat the process for one more hmm, and draw another semicircle on this side of the gap. That's it. Definitely do not draw these lines. Okay, all you need to draw are these three semicircles using a compass. Please use the compass. Okay, another harbor has a much wider gap between its walls. Describe and explain how the pattern of the wave crests in this harbor is different from the pattern you have drawn. If you increase the gap, once you increase the gap, what happens to the pattern of the waves that have diffracted? You'd say that they could be straight. Why would they be straight? If you have a much larger, a much wider, a very wide gap, as the waves pass through this very wide gap, they remain straight. If they pass through a narrow gap, they become semicircular. If they pass through a very wide gap, they remain straight. So you have now straight waves. Why do we have straight waves? Because the diffraction has decreased. Okay, the diffraction has decreased significantly. Okay, much less diffraction, much less. You have these straight waves with the curves at the end. Hmm. Sound wave of frequency 850 hertz travels through the seawater. The speed in the seawater is 1500. Calculate the wavelength. Okay, that's easy. Speed equals wavelength times the frequency. So the wavelength would be equal to the speed over frequency. The speed is 1500 divided by the frequency, 850. 1500 divided by 850 would be 1 point 1500 divided by 850, 1, 1.76, okay, 1.76 meters. 1.76 meters. Okay. Hmm. Figure 6.1 is a full-scale diagram of a lens and an object O. The focal length is 3.5. On figure 6.1, draw the two principal focuses. Okay, measure 3.5 centimeters wherever 3.5 centimeters is. For example, it's on this, okay, this point and at this point. So you have to measure them using your ruler, please. Okay, distance 3.5 centimeters on either side of the lens, focal point and the other focal point. And then draw three rays to locate the image. Draw an arrow to represent the image. So for this question, which is quite rare, you're never required to draw three rays. But again, okay, so what? No problem. I will draw three rays. Okay, drawing three rays. I think this will have this image will be smaller. I think. Okay, let's draw them, or it might be larger. I think the focal point will be a bit further away. 3.5 centimeters might be at this point. Okay, and 3.5 centimeters might be even further away from here. Okay, the first ray, parallel. Again, you're drawing using your ruler. Okay, at this point, once it reaches the center of the lens, what happens? It refracts and passes through the focal point, hmm, or the principal focus. I think you need to draw more accurate lines. Yeah, drawing the line passing through the focal point needs to be a lot more accurate. Anyway, the second line would pass through the center. Okay, passing through the center. Okay, extend the line until they both meet on the other side. Okay, and the third line would pass through the focal point, and then it will move parallel, and they will all intersect at the same point. They will all intersect at the same point. So this is the point of intersection. We have to draw the image. How can I draw the image? The image would be an inverted arrow. This would be the image, inverted, real, and in this case, I guess it's larger. Oh, say three properties of the image. I just said them. Inverted, real, and large. And large, enlarged. Hmm. Student incorrectly states that this lens is being used as a magnifying lens, magnifying glass. State how the image produced by a magnifying glass is different from the image eye. How is the image produced by a magnifying glass different from the image eye? Any image being produced by a magnifying glass has to be what? It has to be, yes, it can never be real. It has to be upright, it has to be enlarged, it has to be virtual. So it has to be virtual and upright. Any magnifying glass. The student moves the object to position P so that the lens shown in figure 6.1 acts as a magnifying glass. On figure 6.1, mark a possible position for P. How can this same lens act as a magnifying glass? So the object needs to have a distance much less than the focal length. So for example, I would place the object at this point, P. I would place the object at this point, P. Yes. Okay? Yeah, the distance has to be closer to the lens than or shorter than the um, focal length. Hmm. Define. Okay. How can we define the electromotive force? Electromotive force had an old definition, okay, and now has a newer definition. What is the newer definition? Or if you think about the electromotive force, we've always talked about electromotive force as being what? As being the work done. There is work done on the charges and there is work done by the battery, electromotive force. So if we're talking about the electromotive force, so we need to talk about the battery. What does the battery do? It's the electrical work done by the battery or by the source in moving the charge around the complete circuit. So it is the work done, okay, by the source, hmm, in moving the charge around the circuit, or around the complete circuit. Figure 7.1 shows a circuit, okay, work done by the source, electromotive force. If you asked about the potential difference, it would be the work done on the charge. Oh, but okay, now we have two lamps which are identical. Each lamp has a potential difference of 3 volts. 3 volts. And the current 2 amperes in it. So the current is 2 amperes. Current is 2 amperes. Calculate the value of R. The resistance PQ is R. So the resistance here is R ohms. We do not know the resistance. Can I find the resistance? Yes, okay, that's easy. Do I have the voltage? So R equals V over I. Do I have the voltage and do I have the current? Yes, you do have the voltage and you do have the current. If the voltage was 3 volts in these lamps, so if I want to draw, for example, a voltmeter, you don't need to draw a voltmeter. If you draw a voltmeter across PQ, the voltage would be 9 volts. The voltage would be 9 volts. What about the current? It's 4 amperes. Why is it 4 amperes? Because he said 2 amperes in each of these lamps. Each lamp has a potential difference of 3 volts, and each lamp has a current of 2 amperes. So the total current is 4 amperes. The total current is 4 amperes. So basically, all you need to do is R equals V over I. R equals V over I, so 9 over 4, which is around 2.25. So R equals V over I, 9 over 4, which is 2.25 ohms. Another piece of wire is made from the same metal. The length of the new piece of wire is twice the length. The diameter is twice the diameter. Ah, now he's talking about the diameter. So the length, we know that the length is directly proportional. So when the length is multiplied by 2, the resistance is also multiplied by 2. Okay, that's easy. So the resistance was initially 2.25. You will multiply it by 2, which would be 4.5. Okay, that's good. 4.5 ohms. That's the first part. The second part, when the diameter is multiplied by 2, twice the diameter, what happens? Diameter is multiplied by 2. The resistance, well, first of all, the diameter or the area is inversely proportional to the resistance. As the area increases, the resistance decreases. Okay. The diameter and the radius are also inversely proportional. Diameter and the radius are also inversely proportional, but with a square factor. So if the diameter is multiplied by 2, the resistance is divided by 2 squared, which is 4. So the resistance is divided by 4. So now the resistance is 4.5. You divide it by 4. 4.5 divided by 4 is 1 point something. 4.5 divided by 4 is 1.125. So the total resistance now of this new um, wire would be 1.125, 1.13 ohms. 1.13 ohms. Okay? Not bad. Okay, question 8. A. State the difference between an analog signal and a digital signal. Hmm. Difference between analog and digital. How can I draw the diagram? For example, a digital signal would have only values of 1 to 0, so it's either 1 or 0. 1 or 0. Okay, 1 or 0. That's it. Actually, the probability of this being in your actual final exam is now quite high. Why? Because for years and years they have not asked about this question, and lately they've figured out why don't we. So they have included more of these questions, analog and digital signals, in the past year. So we need to freshen up our memory. This is a digital signal. Okay, this is the digital signal, and the analog signal could vary. Okay, could vary. It could increase or decrease between any values. Okay, this is an analog. How can I write it down? How can I? Digital signal. It's either high or low, 1 or 0. Analog can have any value or can vary between two values. Digital. Only values of 1 or 0. High or low, on or off. It's like a switch. It's either on or off. The analog signal hmm, can vary between two values. It's like a variable resistor, like a variable resistor, potentiometer. Draw the symbol for NOR gate. Definitely this is cancelled. And this whole page is also cancelled. You're in luck today. Hmm. Question 9. An X-ray machine requires supply of 110 kilovolts. The main electricity supply is 230. A transformer is used to supply the correct voltage to the X-ray machine. X-ray needs a supply of 110,000 volts. The main supply is only 230 volts, so basically you need to step up this transformer. There are 50 turns on the primary coil. Can I find the number of turns on the secondary coil? Yes, you need to increase the number of turns. So basically Vp over Np equals Vs over Ns. Vp is 230 over 50 equals Vs, which is 110,000 over Ns. If we cross multiply 50 times 110,000 divided by 230, the final answer would be around 23,913. So you can just write it down as 23,900 turns. You can round it up to 24,000 turns if you'd like. Draw a labeled diagram of a step-down transformer. On the label, state the suitable material for each of these components. Okay, this is a quite a gift, I guess. 5 marks. Okay, they have given you 5 bonus marks. We need a core made of iron. This is a step-down transformer, isn't it? Okay, so this is an iron core. Iron core. And then step-down transformer means that you have more coils on the primary coil and less coils on the secondary coil. This is the primary coil, and this is the secondary coil. صح? Secondary coil made out of copper. Made out of copper. Okay, made out of copper. So that's it. And you have more turns on the primary coil, which is quite obvious from this drawing. Explain how a transformer operates. That's easy. How does a transformer operate? Um, we kind of memorized the steps or the operation of any transformer. How does it operate? First of all, you need an AC, right? You need an alternating current in the primary coil. So the alternating current in the primary coil. What does it do? Hmm, The primary coil creates an creates an alternating magnetic field. So an alternating magnetic field which keeps on cutting, which cuts. You have to say that cuts. This is one very, very important keyword, which cuts the secondary coil. The secondary coil, inducing an alternating current in the wire. Hmm. Inducing an alternating hmm, current and EMF in the secondary coil. That's it. You have to talk about the current being alternating. That's a must. And then you have to talk about the cutting, magnetic field being okay, cutting. And then you have to say that the current is induced in the secondary coil, or that the EMF is induced in the secondary coil. Okay, three very important points. All good? Okay, question 10, figure 10.1 shows a beam of radiation in a vacuum. The beam contains alpha particles, beta particles, and gamma rays. The beam of radiation is moving this way. The region of uniform magnetic field is out of the page. Okay, so the region is out of the page. So using Fleming's left-hand rule or Fleming's right-hand rule, let's start off with the left-hand rule. First finger, the index finger, is the magnetic field. Magnetic field is out of the page. Magnetic field is out of the page. The second finger, which is the middle finger, is the direction of the alpha. I'm talking about the Fleming's left-hand rule. Left-hand rule is alpha. Right-hand rule is gamma. Sorry, beta. Left hand rule is alpha, right hand rule is beta, or you can just use the left hand rule and say that the beta is in the opposite direction. Anyway, if the alpha is out of the page, if the magnetic field is out of the page and the alpha is moving to the right, so the alpha is moving to the right, so the force on this alpha will be downwards. The force on the alpha will be, it will bend downwards, and we need to label this alpha. Okay, so alpha particles and label it alpha. Beta particles, okay, so alpha, it will take a long deflection, quite a strong deflection. This is alpha. What about the beta? It would be a much stronger deflection. This is a weak deflection, this is a stronger deflection, and it will be upwards. Why is it a weaker, or why is it a stronger deflection? Because the beta is much, or the alpha is much more heavier, so it takes a longer time. It takes a longer time to pull the alpha downwards. Anyway, and the gamma definitely will be unaffected and will continue in a straight line. These are the gamma rays. Then Fleming's left-hand rule for the alpha particles. Radioactive sources have many uses in medicine. State two safety precautions which hospital staff take when working with gamma sources. We have several safety precautions. What are some of the most important safety precautions? First of all, you need to use a protective barrier. Second of all, you need to use or you need to decrease the time of exposure. You need to keep a large distance. Okay, use a protective barrier. Okay, barrier. And decrease the time of exposure, decrease time of exposure, can say increase the distance, store in a lead container, okay? Hmm. Question C, radioactive isotope iodine 131. The nucleus of iodine contains 53 protons, 78 neutrons. Can I draw? I'll use the nuclide notation to show the isotope of iodine. Yes, I. And then how many neutrons, how many protons do we have? 53. So write down 53. And I'll just write down 131 on the top because this is the nucleon number. Or you can add 53 plus 78, which is again 131. Iodine 131 emits gamma radiation. Its half-life is 8 hours. Explain why this emission and this half-life makes iodine a suitable material for a tracer in medical diagnosis. Why would this be a suitable usage of the iodine? Why do we use iodine? Hmm. Yes, because the gamma radiation can, yeah, it can penetrate through the body and it can be detected outside the body. Okay. If we talk about the half-life isn't too short and isn't too long. It is short enough that it wouldn't affect the patient on the long time, on the long term, and it's long enough to be detected by the detectors. Okay, so we can say that the gamma radiation can be detected outside the body. Okay, outside the body. And you need to say, for example, that the half-life is short, so won't affect the patient on the long time, on the long term, on the long term. Again, it's not long enough as well. It's long enough to be detected. It is long enough to be detected. Okay, good.